Kirsty Duffy, and I'm back with my favourite dessert, ice cream, to talk about my favourite fundamental friends, neutrinos. Neutrinos are very sneaky little particles, but they're much sneakier and stranger than anyone expected, as scientists realised when a bunch of neutrinos from the sun appeared to go missing. Unravelling the mystery of what happened to them revealed one of the strangest features about neutrinos, and that's what we're talking about today on Even Bananas. Let's set the scene. It's the late 1960s in South Dakota. There's a man with 100,000 gallons of dry cleaning fluids, and he is a mile underground in the largest gold mine in the Western Hemisphere. Clearly, he's studying neutrinos. That man was Ray Davis, and he and his team built an experiment to measure neutrinos from our most illuminating natural source, the sun. Physicists in Davis's day had some pretty successful models that explained how the sun produces neutrinos by the same nuclear fusion processes that produce light. That meant they could predict how many neutrinos would be emitted by the sun. So Davis and company set out to detect those solar neutrinos and show that the sun is powered by nuclear fusion. To do that, they built a massive detector the size of 3 double-decker buses. Quadrillions of neutrinos arrived at the underground detector every second, completely unaffected by the thousands of feet of rock above it. And, more often than not, the detector itself. Rude. On the rare occasion that a neutrino hit one of the chlorine atoms in the liquid, it would transform that chlorine atom into a radioactive argon atom. By extracting those argon atoms, researchers could figure out how many neutrinos were arriving at the detector from the sun. Even with this gigantic detector, the team was seeing just one argon atom every few days. The experiment worked great. The scientists proved for the first time that neutrinos are produced by the sun. But there was a problem. They only detected about 1/3 of the neutrinos they expected to see. This became known as the solar neutrino problem, and it wasn't fully resolved until about 20 years ago. To picture why the solar neutrino problem is so puzzling, imagine your friend has 3 bananas and passes them all to you, but you're only holding 1 banana after they do. At first, many scientists just assumed that something was wrong with Davis's experiment. Detecting individual argon atoms is hard. I mean, I can barely find my keys. Maybe his experiment just wasn't seeing all of them. But the experiment ran for more than 20 years and consistently got the same result. It just didn't seem to make any sense. What was happening to the rest of the neutrinos? Other scientists thought that something was off with the models of the sun, but when they checked, nobody could find any mistakes with the calculations. So the experiment worked properly and the calculations were good. A bunch of solar neutrinos were just missing somehow. Physicists officially had a mystery on their hands. One person who was not surprised about the missing neutrinos was Bruno Pontecorvo, a theoretical physicist. Ever since scientists had discovered that neutrinos come in 3 flavours, Pontecorvo had been wondering, what if they could change from one flavour to another? Through the magic of fusion, the sun only generates electron neutrinos, so that's what Davis's experiment was designed to measure. But if neutrinos could shapeshift between the 3 flavours as they travelled, some of them would seem to disappear because the detector was only looking for the one kind. Like a detective missing a suspect because they're in disguise. It turns out this is exactly what happens, and in 2001, an experiment at the Sudbury Neutrino Observatory in Canada proved it. The researchers at Sudbury found a way to measure certain interactions caused by just electron neutrinos and other interactions caused by all the neutrino flavours. So scientists could finally measure the total number of solar neutrinos and compare it to the number of solar electron neutrinos. The total number of neutrino interactions matched the predictions for what the scientists expected the sun to produce. And the electron neutrino interactions match what Ray Davis saw. 1/3 of the total number. As the neutrinos travelled from the sun, 2/3 of them had changed, from electron neutrinos to the 2 other types. Scientists had officially discovered a phenomenon where neutrinos could change their flavour. It's often called oscillation, but there's a bit more to it. In 1998, an experiment in Japan called Super Kamiokande, or Super K, was measuring muon neutrinos created in the atmosphere, and they also saw muon neutrinos seemingly disappearing. But even stranger than that, the Super K researchers found that the farther the muon neutrino had travelled, the more likely they were to have disappeared. That proved that neutrinos don't just change flavour, they actually change in a very specific back and forth kind of way. That means what form we catch them in depends on how far they've travelled. Even today, there's a lot that's still a bit mysterious about neutrino oscillation. It is a very weird phenomenon, even for people who think about quantum mechanics all day. The standard model of particle physics, our gold standard theory for understanding the subatomic world, can't yet explain it. So the experiments to try to understand neutrino oscillation continue. Answering some of physicists' remaining questions about oscillation will be one of the major goals of the Deep Underground Neutrino Experiment, or DUNE, currently under construction at Fermilab. Over the next few episodes, we'll talk more about what scientists already know about neutrino oscillations and what's still unknown. Buckle up for a whole lot of quantum weirdness. Don't forget to like, share and subscribe so you get notified when we do. And in the meantime, what's your favourite neutrino mystery? Let us know in the comments. Fun fact! The mine where Ray Davis set up his solar neutrino experiment is still an important research facility. It's now called the Sanford Underground Research Facility, and it's going to house the FAR detector for DUNE. The Underground Lab's contributions to neutrino science will come full circle in the late 2020s.